Hi, I'm Natalia Sheblever, researcher in Software Competence Center Hagenberg and PhD candidate in Institute for Machine Learning in Johannes Kepler University in Austria. I would like to present you work which was done together with my colleagues named ReLU Code Space, a basis for rating network quality besides accuracy, as a part of Machine Learning Summer School Tübingen 2020 Poster presentation. In this work, we propose a new metric space which in the future can be used to rate quality aspects of ReLU networks besides the traditional quality indices used to choose between models in NAS. This work is a part of ongoing research on security and safety for shared artificial intelligence project, and it was first presented on iClear 2020 workshop on neural architecture search. Both paper and code are available online. Finding best architecture and hyperparameters for a given dataset is not an easy problem. NAS systems define a set of quality indices by which this selection might be done. As example, this impressive work for Chris of Christian showed how difficult the choice is by training 5 million models on Cipher10. We have our toy example as well. This is validation accuracy of VGG16 trained on MNIST. All configuration training parameters are same except the learning rate. In both cases, as you can see, accuracy is very close to 1. So here comes the question, which network I have to choose in this case? Unfortunately, we don't have answer yet to this question. But what we can do right now is to investigate what is happening inside the network. Inspired by Montefior's analysis of ReLU networks complexity, we focus on fully connected layers of ReLU networks. With that, we propose a new metric space, ReLU Code Space, which establishes an isometry between ReLU activations transformed to codes and polyhedral bodies in the input space. So what is this metric and how we define it? First, we define ReLU network as a function which maps input space M to output space N. The activation vector A for an input X at layer K will be an element-wise multiplication of ReLU and linear activation GK, which consists of weights and biases. With that, we can define a code for input X as a binarized activation function. Based on that, our ReLU code space is a metric space consisting of the set of induced codes and Hamming distance between codes induced by input vectors x and y. By having Hamming distance in mind, we can establish duality representation theorem of ReLU codes, which states that there is a one-to-one correspondence between the code space and the set of equivalence classes. The set of the equivalence classes is a tessellation, and a topological closure of equivalence class is a polyhedron. In other words, the intersection of a finite number of closed half spaces, or in other words, is actually our ReLU activations. Using truncated Hamming distance, we can define the adjacency metric space. If the adjacency is 0, then our inputs belong to the same polyhedral cell. If it's 1, then polyhedral cells are distinct and adjacent, and distinct and not adjacent if distance is 2. And if distance more than 2, we actually don't know what's going on because it's an n-dimensional space. Therefore, all the distances then higher than 2 for us is 2. Based on that, we can formulate ReLU code space isometry theorem, which establishes an isometry between adjacency metric space and ReLU code space. To prove our concept, we perform all experiments on 2 architectures, autoencoder and VGG16, analyzing only encoder part of autoencoder and fully connected layer of the VGG16. Moreover, we varied number of layers and amount of nodes in each layer. As for the dataset, MNIST and Cipher10 were used. Also, as for all NAS papers, we put same binary initializer, kernel seed, random seed, and we documented all of that. Coming back to our toy example, where only learning rate was changed. Both networks are indistinguishable with respect to accuracy, but the number of cells of the induced tessellation shows a different behavior, as you can see. Unfortunately, we're still not able to say which network generalized better. However, characteristics of the tessellation and their correspondence in the ReLU code space can be helpful for deriving novel quality measures. In our second experiment, we vary only architectures and number of code as shown in the setup. To visualize clusters of ReLU codes, we used UMAP. Important to note that the all clusters are shown with respect only to the ground truth but not the output layer. As you can see for the autoencoder, features of higher layers learn more invariant features than lower ones. And this behavior we were looking for, and this is behavior we were expected. And we are very glad that we get it. For VGG16, we see absolutely opposite effect regardless of number of layers. This indicates that binarized ReLU codes contained the essence and essential information for discrimination between the networks. However, which one? We're not 100% sure yet. So, as you can see, we propose a new metric space. We performed and proved our concept by having experiments on MNIST, CIFAR, VGG, using VGG and autoencoder. And of course, since it's an ongoing research project, there are still many questions. For example, which kind of information is in fact stored and how much of the important information will lose by binarization? What does backbone and other regularization technique, how do they really affect our code space? How we can address the comparison to the output layer? How can we address comparison to other activation function? Can we represent tessellation in the graph structure and what can we get from it? For all of these questions, I will just continue my research. And if you're interested in what you just saw, please have a look at the paper. And if you have any questions or you really would like to discuss something, please don't hesitate to contact me. Thank you very much for your time. Bye bye.